is happening to this particular body, is it moving or is it stationary. Okay. Let us look at the first question of it being stationary. Okay. If it is being stationary, we say that the acceleration is equal to 0. It is a principle of statics that we use right now. It is not rotating, which means the angular acceleration is 0. It is not moving in the x or y direction, which means those two accelerations are equal to 0, and if we apply the principle F equals m a, mind you I am writing this as vectors, this m is the mass of this particular rigid body. If this is equal to 0, we get F equal to 0, and this is one equation. The other equation has to do with the moment is equal to I times alpha, where alpha is the angular acceleration of this rigid body. I am just writing it as scalar, but it is something that is about an axis that is we can find out the relationship between the forces and moments by solving these equations. We can solve for these values once we know the forces acting. Take what in this constraint. Okay, we call those as reactions. So in this particular rigid body, this hinge will offer two reactions. I am going to represent this as x and this as y. So I will have one reaction like this. Let us say this is A and this is B, and this is point C. We will have a horizontal component of this. So let me call that as Ax, and there is a vertical component of this reaction Ay, and there is a particular direction to this. So let me just represent the direction. Okay, let us say this is around, this angle is theta with respect to vertical. So I can represent this as the force B. Okay, mind you, in this particular case I know at what angle the force is acting, which means only the magnitude is an unknown. Here the two unknowns are Ax and Ay. Okay, so if I complete it, this shows the free body diagram. Okay, This free body diagram is essential in order to solve for the unknowns using systems of equations. Okay. So, let us write it down. If I am looking at statics, I know that each of these components the resultant components have to be equal to 0. Okay. So, I have to convert this into for the same rigid body, assume this is the same rigid body that I am drawing. I have force here, force here, force here, force here, and a force over here. Let us say the resultant force is acting like this, and this is vector F. I am taking a point over here which is, let us say, O. We will come to what point to take at a later stage, okay, and a moment m at O. Okay. If this is stationary, the force should be equal to 0, the vector itself should be equal to 0. And if I take a vector that is outward to the board, that is a positive direction. So, if I have a vector outward, the moment is going to be anti-clockwise, which is taken to be positive. So, one way of doing this is I can write Fx, or the component of this force along x direction, which is this positive is equal to 0, this is a positive quantity, this is equal to 0. I can do the same thing over here, m at O taking anti-clockwise to be positive is equal to 0. By doing this, we will not miss out on the sign conventions. For example, in this particular case, this particular force P is trying to rotate about this point O in a clockwise direction, okay, which is negative of anti-clockwise, and you can see here d1 is a positive number, P magnitude is a positive number, which means I will have a negative sign over here indicating that it is actually a positive clockwise value represented by anti-clockwise, okay. You can do the same exercise for each one of these. One of the advantages of planar problem is all I need to do is to find out the distance of the vector direction to a particular point in question. For example, if this is the body, if this is the force B, I can extend this line, find out what would be the perpendicular distance of O with respect to this B, okay. Let me call this as d1. Again, if you notice, the force is such that it is acting to rotate the body in the clockwise direction. So, I will get a